Hello, in this video lecture today, we shall do qualitative study of laser. Laser is the short form of light amplification by stimulated emission of radiation. The central phenomena of laser is the stimulated emission. It was coined by Albert Einstein in 1917. Laser was the second invention after maser, which was the short form of microwave amplification by stimulated emission of radiation. In this, I shall explain the coherence of light, stimulated absorption and emission, and spontaneous emission of radiation. Few examples of laser will also be discussed after explaining the principle behind laser production. So, the theoretical basis for the development of laser was provided by Einstein in 1917. Einstein's prediction was put to practical use after 1954, and in 1960 the first laser device called ruby laser was developed. It was a solid-state laser. The first gas laser was helium-neon laser. The most important features of laser are the high degree of coherence, the high directionality, extraordinary monochromaticity, and very high intensity. Next, we shall discuss about these. These are the properties of laser, like very high intensity, high directionality, coherence, and monochromaticity. Unlike ordinary light ray from ordinary bulb, which diverges in all the directions, laser diverges very less. By saying this, one means that the spot size of laser beam increases very little on moving a very large distance in direction of the laser. Furthermore, this small divergence angle is due to diffraction because the laser has to pass through a small aperture of the source. The divergence angle of laser depends on the diameter of this aperture and the wavelength of the laser. And this relation is the divergence angle equal to 1.27 lambda divided by diameter d. Due to divergencelessness, a laser is highly directional. It is the high directionality of the laser which enables us to use laser in distance measurement of the distant objects. Next, unlike ordinary light rays, laser does not contain many wavelengths. A laser is highly monochromatic light. The monochromaticity of a light wave is also sometimes defined by its bandwidth. The bandwidth of LED light, for example, is 30 nanometer, while that of mostly used helium neon laser is only 0.2 nanometer. The bandwidth of laser is very less, which is also related to its coherence. Before talking about coherence of laser, let us first know what the coherence is. An ordinary light ray is the bundle of many sinusoidal waves. Each sinusoidal wave has a phase relationship up to a very short period in space and time. The ordinary light has no phase relationship. So, the coherence can be defined as the extent of phase relationship. If by information of phase of one wave, the same of the another wave can be predicted, then we say that these two waves are phase coherent. Most of the times, this is said in other words, that two waves are coherent if their phase difference is constant over the time and space. Clearly, for two different waves, both the statements are the same. But what about a single wave? Coherence of single wave can also be defined in the similar way. If by information of phase of wave at one point in space or time on the wave, the phase of another point in the space or time of that wave can be predicted, then this wave is said to be phase coherent. Like here, in this figure, this wave is composed of as many parts of sinusoidal waves. So if we know the phase at this point, we can tell the phase of this point also by measuring distance from this point to this point. But if by information of phase at this point, somebody asks about the phase of this point, we cannot tell because there is a gap or there is a break in the wave here. So what phase difference this break will introduce, we don't know. So this wave is coherent only up to this point to this point, or this point to this point, or this point to this point. So the coherence length of this wave is not greater than this length. But in this way, if we know the phase of this point, we can tell about the phase of this point, or this point. This wave is coherent from this point to this point. So this is the coherence length of the wave. The distance and time up to which a given light wave retains the phase relationship is called the coherence length and coherence time respectively. The coherence length can also be called as the length of single sinusoidal wave in the light beam. The relation between them is this: L phi is equal to c, which is the speed of light in space, multiplied by coherence time. As an example, the coherence length of an ordinary neon light is about 3 centimeter, and so the coherence time is around 10 to the power minus 10 second. On the other hand, the coherence length and time for the laser beam are very large. For a well-controlled laser, the coherence time can be as great as 3 milliseconds, giving the coherence length of 900 meter or 0.9 kilometer. This coherence length is important in telecommunication engineering. The bandwidth in terms of frequency is theoretically zero for a wave with infinite coherence, while that for wave with finite coherence time is non-zero. The coherence time and frequency bandwidth are related as this, or we can say that the coherence time and frequency bandwidth are inversely proportional to each other. And by this relation, one can find relation between wavelength bandwidth and coherence length. These are few examples of coherence length and coherence time. For sunlight, coherence time is 2.67 femtoseconds, and so coherence length is only 800 nanometer. But for sodium lamp, coherence time is 2 picosecond and coherence length is 600 micrometer or 0.6 mm. For helium neon laser, coherence length can be up to 20 meter. So, laser is highly monochromatic and highly coherent light beam with very extraordinarily high intensity. Now, let us talk about some basic concepts important for laser, like absorption of light by matter and spontaneous and stimulated emission of light and population inversion. Now consider that an atom has two energy levels, E1 and E2. The energy of ground level is E1 and energy at the excited level is E2. So the energy difference between these two energy levels is E2 minus E1. If a light photon of energy h nu equal to E2 minus E1 is incident on this atom, this can be absorbed to excite an electron from level 1 to level 2. This is known as stimulated or induced absorption of the light. This absorption depends upon the incidence of light photon. So, the probability of stimulated absorption is directly proportional to the incident energy density. Here, with the energy density, we mean that how many photons are incidenting on the atom per unit time. And this absorption also depends upon the characteristics of excited and ground states. So, if we denote probability of stimulated absorption by P12, and this probability is directly proportional to the incident energy density. Here, this can be written also as P12 equal to B12 multiplied by energy density. Here B12 is proportionality constant and it is known as Einstein's coefficient of stimulated absorption. Once a photon is absorbed and electron has reached to its excited state, it cannot be there for a long time. So after a very short lifetime of 10 to the power minus 8 seconds, it returns to its original state. And this energy difference which was absorbed by it previously is emitted by it. This emission is known as spontaneous emission. And for this to happen, there is no need of external stimulate. So the probability of this spontaneous emission does not depend on anything, and it depends only upon the characteristics of these two energy states. So this probability of spontaneous emission is constant. That constant is represented by A21. This constant is known as Einstein's coefficient of spontaneous emission. The light photon emitted in this way are the main source of ordinary light. There is another type of emission also, which gives a highly coherent light. During the time an atom is in excited state, if a photon of the same energy difference h nu is allowed to incident on this atom, the emitted photon by the atom's jump to lower energy state moves with the incident photon. The direction of propagation, phase, and energy of the emitted photon are exactly same as that of incident photon. Therefore, the result is an enhancement of beam of coherent light. This process is called stimulated emission. So, in this stimulated emission, it is necessary that when an electron is coming from higher state to lower state at the same time, external photon of the same energy difference is incidenting on electron. So the probability of stimulated emission is directly proportional to the incident energy density. It can also be written as the probability is equal to B21 multiplied by energy density. Here B21 is known as Einstein's coefficient of stimulated emission. So in stimulated absorption, the incoming photon is absorbed by the electron in ground state like this, and the electron jumps to the excited state. This process is known as stimulated absorption. After stimulated absorption, the electron stays in excited state for a very small time duration, and then it returns to its ground state by releasing a photon. This process is known as spontaneous emission. There is another possibility after stimulated absorption. In this, once stimulated absorption is complete, then after staying here for 10 nanoseconds, when this electron returns to the ground state, at the same time, if the system encounters incoming photon of the energy equal to the energy difference between these two energy levels, then this happens. In this process, the emitted photon goes along with the incoming photon. The phase, direction of propagation, and energy of both the photons are identical. In this way, we can produce the phase coherent photons. This process is known as stimulated emission. So, as a whole, in the stimulated absorption, a photon is absorbed. In spontaneous emission, the photon is released in random directions, and in stimulated emission, the released photon has the same phase, same direction, and same energy as that of stimulating photon. So here we represent stimulated processes by B and spontaneous processes by A, and 1 2 and 2 1 represent the direction of transition of electron in the process. So we have the probabilities of stimulated absorption, spontaneous emission, and stimulated emission. And these are the Einstein's coefficients. It is clear that total probability of emission is summation of spontaneous emission and stimulated emission probabilities. These are the relation between the Einstein's coefficients. This relation says that the coefficient of stimulated absorption and stimulated emission are the same. And this expression says that for higher values of frequency, the value of coefficient of stimulated emission will be less. And as we know that stimulated emission is responsible for phase coherent waves, so it can be said that the laser of high frequencies are difficult to produce.